Okay, next we are going to talk about section 4.3. This is monotonic functions and the first derivative test. First we are going to talk about what the monotonic function is, and then we are going to talk about the first derivative test and the use of that test. Alright. So we talked about the increasing function, decreasing function. Being monotonic means if a function is increasing, it's going to be increasing everywhere. It's on that interval. It's called monotonic. So if a function is always increasing or it's always decreasing, then it's called monotonic function. That's the definitions. Okay, that's the definition. Let's look at this corollary 3 and let's understand what this means. So let's say f is a continuous function on the closed and bounded interval and differentiable on the open interval. These are the conditions that we have for the mean value theorem, remember. This corollary says, actually by looking at the derivative of f, we can easily conclude whether f is increasing or decreasing. That's a very nice corollary actually. If you take the derivative of f, if the derivative is always greater than 0 for each x in the open interval, then f is definitely increasing function. If you take the derivative of f and if you see that the derivative is always negative in that interval, then f is definitely decreasing on that closed and bounded interval. So that's very nice. By just checking the derivative, you can easily get that whether the function is increasing or decreasing. Alright, so let's practice that here. Okay, this function f is given x cubed minus 12x minus 5, and we want to know where this function is increasing or decreasing. Okay, so we have this f and we want to show where this f is monotonic. Actually, as you would see, the function is increasing here till negative 2 here, x is equal to negative 2, and then it's going down here till 2, x is equal to 2, and then it's going up here afterwards. Okay, so so f is monotonically increasing here, monotonically decreasing here, and monotonically increasing here, as you would see. But how are we gonna do that without seeing the graph? You have to take the derivative of this, and you're gonna look at x values where f prime is positive. That's where you're gonna get that f is increasing. And you're going to look at the x values where f prime is less than 0. This is where the graph is decreasing. You're going to find that between negative 2 and 2, the derivative is negative. See the tangent line here? All look at the take any point and draw a tangent line. It's a tangent line with negative slope, and any tangent line here is has a negative slope. If you take a tangent line here, then this tangent line has a positive slope. Here, positive slope, which means derivative is positive. Here, if you take a tangent line, it's the derivative is the tangent line. The slope is positive, which means the derivative is positive. Okay, that's how you would see that. Then we draw such a table to show that. Of course, you have to do some sort of computation. And I'm going to show you in written way, in handwritten paper, and explain again. And between negative infinity to negative 2, since the derivative, take any point in between and take the derivative of f, of course, put it in. For example, negative 3 is in here. Put it in, you're going to get a positive value. So for any arbitrary x in here, you're going to get a positive value here. So since the derivative is positive, function is increasing here. Look, behavior of f, it's increasing. You look at the sign of f prime, it's positive. You evaluate f prime and find the value by just taking sample point in here. Similarly for decreasing, we just look at between negative 2 and 2. Take the derivative, pick a number in between, say 0. You can take 1, you can take negative 1, put in f prime, you're going to get a negative value. So this negative value is going to tell you that the sign of f prime in this interval is going to be always negative. If the derivative is negative, then this means behavior of f is, which means the f is gonna be a decreasing function here. After 2, x greater than 2, you take the derivative of f, pick any arbitrary point bigger than 2. In this example, they took 3. So if you put it in, you're going to get 15. 15 is a positive number. This is going to tell you that f prime is always positive after 2. And if the derivative is positive, corollary says that f is increasing. So we are done. Look, the red part is decreasing part, the green part is increasing, your green part is increasing. This table is very useful. And okay, next I think we are going to learn about first derivative test. Okay, so what's first derivative test? So let's say we have a continuous function f and differentiable function in an open interval and containing a point c. This c is a critical point of that function f. Okay, so moving across this interval from left to right, the interval a to b, if f prime changes if the derivative of f is changing sign from negative to positive at c, then f is a local minimum at c. If f prime changes sign from positive to negative at c, then f is a local maximum at c. If f prime doesn't change any sign, then f has no local extremum at c. Okay, so that's what we have here. So let's see that in here. So this function f, we have the ab, we have absolute minimum here, local minimum here. This is the smallest of them all. We have absolute maxes here. Okay, so let's look at between a and c1. Look at that f is increasing. That means if the derivative of f is greater than 0, and then after c1, the derivative of f is still bigger than 0 because f is increasing, right? So here we have the first derivative is 0. We don't have a local max or local min because of that. Okay, even if f prime is 0 here, no extremum, because to the right there are some y values that's bigger than this point, and to the left there are some values of f that are smaller than this value, y value here. So you don't have a local max or local min here. Okay, this is like by x cubed. Y is equal to x cubed, right? In y is equal to x cubed at 0, there's no extremum. And then if you continue, after c2, the derivative is negative. Before c2, the derivative is positive. The first derivative test says if before c2 the derivative is positive and after the derivative is negative, then you have a local max here. That's what the first derivative tests say. Okay, you have at c2 we have the derivative 0, which is going to tell us that c2 is a critical number, right? Critical number means first derivative is 0 there, right? c2 is a critical number and it's a local max. Then we have a local max. Let's go back to the theorem, the first derivative test. So we have a local max if the f prime changes from positive to negative at c. Yes, the first derivative changes sign from positive to negative at c2. So we have a local max. Let's find a local min somewhere. Where is local min? Here. Let's get around c3 before and after. Before the derivative changes sign from negative to positive. So by first derivative test, we have a local min here. Okay. So these are examples. These two are examples for a first derivative test. And if to the right and to the left, there's no change in the sign of f prime. Look, to the right and to the left of c1, even if it's a critical number, if the derivative doesn't change in a sign at c1, so no extremum. That's what the third condition says. If f prime doesn't change sign at c, then f has no local extremum at c. Let's find another example to that. Okay, so before, let's look at c5. Around c5, to the left the derivative is negative, to the right the derivative is negative. So f prime doesn't change sign around c5, even if c5 is a critical number, because f prime at c5 is 0. no extremum according to the first derivative test. Okay, so first derivative test is going to be useful, and this first derivative test gives information on the local maximum or local minimum. Okay, it doesn't give any other information. And let's see, what is this example? Okay, so let's look at this example too in our book. Y is equal to x to the 1/3, x minus 4. Of course, the graph is given. If the graph is given, it's easy, right? So you can easily see that at 1 the function is decreasing till 1, and then the function is increasing afterwards. So it is easy. However, we need to, of course, usually we will not have the graph. If you don't have the graph, what are we going to do? What we are going to do, we are going to look at the derivative. So we are going to take the derivative of this function, and then when you take the derivative of this function, you're going to see whenever it is x is less than 0, the derivative is going to be negative. Between x0 and 1, it is negative. Whenever x is bigger than 1, it's positive. So if the derivative is negative, then f is decreasing. If the derivative is negative, f is decreasing. If the derivative is positive, it is increasing. So we get it actually. Okay, so here so it is decreasing before 1 and it's increasing after 1. But we have to analyze this the point 0, the point 1, and the point 1. I mean the 0 and 1. So where do we get the 0 and 1? When you take the derivative of this, you have at those points the derivative is 0, right? Or undefined. Okay, since we don't have the derivative here right now, I wouldn't say which one is actually at 0. It's a critical point, because if you take the derivative of this, you get denominator. In the denominator you have some powers of x, and this is going to make the derivative undefined. Because of that, it is going to be undefined. It's going to be a critical point, and at 1, at some point, I think the first derivative is 0, so it's a critical point too. Alright, so let's see the next example, which is example 3. In this case, we have this function y is equal to sine squared x minus sine x minus 1. If we know the graph, life is perfect, because we know where the function is decreasing. Here, look at this, it is decreasing, and then increasing, and then decreasing, and then increasing, and then decreasing down here. However, usually, and most of the time, we don't have that. So what you do is you are going to take the derivative of this. For example, take the derivative of this, you get 2 times sine times cosine minus cosine, and then you're going to equate this to 0 and then find the zeros of this function, and actually you get like pi over 6, pi over 2, 5 pi over 6, 3 pi over 2 as the zeros of this function between 0 to 2 pi. As you will see this table, the critical numbers are pi over 6, 5 pi over 6, pi over 2, 5 pi over 6, 3 pi over 2, and are the critical points. And then in between, we use the first derivative test, and we just find out that the first derivative is negative in between, in this interval, positive in this interval, negative in this interval, and positive in this interval, and negative in this interval. And f prime being negative, it's going to make f decreasing. F prime being positive, it's going to make it increasing, like increasing here, decreasing here, decreasing here, and decreasing here. And then we are going to come up with this picture actually. Okay, usually nobody's going to give you this graph, but you're going to build this table, and by looking at this table, you're going to be able to draw this graph. Okay, that's the end of this section. Thank you.